Record. Okay, let's try this again. So today we are doing alternating current. This is a transition from talking about all kinds of electricity and electrical and magnetic phenomena into the world of waves. Of course, there are electricity waves. I happen to be a big fan of one particular frequency of radio wave. There are waves in all sorts of different phenomena in the world around us. Light is a wave. Your x-rays at the doctor is a kind of wave. The radio waves that we use to talk and send Wi-Fi over. Your microwave oven makes waves. On the ocean there are waves. The sound that is coming from my very mouth is a wave. The light that is projecting onto the screen can be represented as waves. Waves are everywhere. Waves are in earthquakes in not Arizona. What you say? There's the wave in a football stadium. That's not quite identical, but that is very analogous. We'll actually talk about that as an example in the when we hit the wave section. But today, let's have that hop over. In the electricity world, waves are something we can do. We can look at and get a start. We're not okay. So there are two phenomena that are related. There's an oscillation or a vibration. That's when a wave happens at one place. And there's a wave, which is what happens when that vibration spreads its energy out through some region of the world, or some medium, we say. AC electricity, for our purposes today, we're going to treat as a vibration. It is an electrical vibration in a wire that we harness to heat an oven or run an air conditioning unit or whatever. Flash a headlight. Everything that we've talked about heretofore, am I using that right, has been direct current. We've been talking a butt ton about batteries. Solar panels also do the same thing. Now we're going to be talking about generators. Your car's alternator harnesses alternating current. And in particular, what comes out of the wall sockets is probably my prime example of an alternator. Every power plant except for solar power, generates alternating current. So this is huge in the world around us as well. And we're going to talk about this as a vibration in electrical voltage. From this, we're going to learn to define some terms. They're going to be useful. Waves are even more complicated version of oscillations because they spread out through a region instead of just being at one place. So let's start simple. Okay. I have kept sine and cosine and tangent out of this class to the greatest extent possible. I cannot talk to you about waves, vibrations, oscillations, AC electricity without mentioning sine waves. Sorry. Sorry, not sorry. They're good stuff. AC, alternating current and the voltage that produces it, a note on that in a second, is a sine wave. That is to say, if you were to hook a multimeter, a voltmeter, up to your wall outlet and measure how voltage changes with time, if you graph that sucker, then you would see a sine function. Very pretty. That would be really hard to do because it varies 60 times a second. You'd be having to write down the numbers on the multimeter really freaking fast. But still, in principle, that's what you would see. A note about the terminology. AC stands for alternating current. I am going to end up saying the phrases AC current and AC voltage a bunch. That's sort of silly. AC stands for alternating current. Alternating current? The way we practically use this is AC is talking about the form of electricity, and I can talk about what property, the current or the voltage or whatever, about that electricity. So I will say AC voltage, AC current, even though it is silly. Previously, everything we've dealt with heretofore has been DC, and I think I probably mentioned the phrase DC current before, direct current, which is silly. Terminology aside, AC is a signal, a power supply, a voltage that varies like a sine wave. And in particular, what's in the wall, if you don't connect anything, is there's no current coming out of the wall sockets if nothing's plugged in. So properly, I should mostly be talking about AC voltage. That's what exists even if there's no device plugged in. If you plug in a device, then the alternating voltage will drive an alternating current. Okay, so that note about the terminology aside, I have to admit I am using, if you look down at what the acronym means, the language is silly. I'm going to use that as we commonly do and pick it up by context. I'm going to ignore the fact that it means alternating current. Terms. The time, write this down, memorize this, be able to state this on an exam. The time to complete one full cycle, one full up and down and back to the midpoint again, that time is called the period. It's not just for grammar and biology anymore. Period is the time. How do we measure period then? How do we measure time in physics? Seconds. Period is measured in seconds. I should also write down, should have written down the symbol for period. Period we call not just any t, but capital T. If I say little t, I'm talking about any old time. If I say capital T, I'm talking about that particular time, which is a full up and down cycle has happened. Okay, the reciprocal, what's reciprocal? What's reciprocal? Opposite in what sense? 1 over, yeah. Flip the fraction. The flipped fraction of period is frequency. Let's think about this for just a hot second. What does period tell us? It tells us time, but time for what? The time of one cycle. If you flip that phrase upside down, the time for one cycle, the time divided by the cycles, that is the meaning of frequency, the cycles per time. If I count 1 second, after 1 second has passed, the voltage in that wall outlet has wiggled up and down 60 times. That's what it means for the frequency of commercial power to be 60 hertz. The symbol, the unit for frequency and its unit, frequency is measured in hertz, which is symbolized Hz, capital H, lowercase z, and its symbol is F for frequency. Okay, so frequency, think about this. Think about the meaning here. Don't get these confused. Period, time to complete a cycle. Frequency, cycles to complete a unit of seconds, 1 unit of time. If you flip a fractions upstairs and downstairs, does it make sense that we can flip the phrases, cycles per second, seconds per cycle? It makes sense that they're reciprocals. Yes, no? Feel okay with this? Okay, so we can write down the equation F equals 1 divided by T, or T equals 1 divided by F. I would prefer that you know what these mean, and then you don't need to have this as something on your note sheet. You can just think about, well, if I've got 5 cycles happening in 1 second, each cycle must take 1/5 of a second. If I've got 1 million cycles happening in 1 second, each cycle is 1/1,000,000th of a second. No duh, right? Okay. In a resistor, current at any given instant is the voltage applied to that resistor divided by the resistance of that resistor. If you apply a sine wave voltage to a resistor, you will observe in it a sine wave current flows. When the sine wave is at its middle, no voltage, no current flows. The bigger the voltage is applied as time progresses, the more current flows. Then voltage goes down, the less current flows. Voltage goes negative, that means which side is higher and which side is lower, electrically flips. Current flows in the opposite direction. Goes back to 0, current stops flowing. If I graphed voltage and I graphed current, I'll see the same shape. You can find the resistance, by the way, therefore, hint, hint, by dividing the peak voltage by the peak current. I mean, you could do this by dividing any instantaneous voltage by any instantaneous current. If you look at any instant in time, find the voltage, any same instant in time, find the current, voltage divided by current is the resistance of what that's going through. Duh, right? It, in practice, though, is easy, I find, to look for the peaks. Those are often labeled. However, looking for the height of the peaks, the most intense voltage, the most intense current, the tops of the, or bottoms, for that matter, of the sine shape, is not always the relevant, important way to talk about how strong the amplitude of a AC voltage or AC current. There is a term called power, which I don't think I've actually even defined for you guys. Power is how fast energy is transformed. Power is wattage. You've probably heard about this engine has so many horsepower. Horsepower is another measure of power. You have a 1,000 watt stereo, 100 watt speaker. That is the rate at which joules are transformed in that speaker, the rate at which energy is coming out of that sucker. Wattage is super important for electricity. You pay for electricity, and the more wattage, the faster your bill is going up. That's not the timer, is it? Excuse me, this is my son's. Is this an emergency? Hello, is this an emergency? My son's school. Okay, sorry. Where am I? So wattage is a very important term. Hello, is this an emergency? I'm at work.
It's Mr. Jeffrey from Aguilar Kid Zone.
Yes, go ahead.
Hey, Nalo came into Kid Zone with his hand hurt. I don't know. It happened during school, but it's really bothered him. And so he's kind of just sitting there. He's been crying for the last like 20, 25 minutes.
Oh boy. I'm really sorry. I cannot come now. I am in the middle of a lecture right now. I will try to contact Sir in between. Thank you. Tell him I love him. Bye. Sorry about that. He apparently squished his hand between a chair and the wall earlier today, and it really is hurting. He feels pain more intensely, I think, than most people do. Power. The rate at which energy is transferred has a very simple electrical way to calculate it. If you multiply the voltage somewhere by the current, remember voltage divided by current, that's resistance. Voltage times current, that's power, the rate of energy transport. What if we multiply a peak voltage by a peak current? Well, when electricity is really being pushed by the sine wave of AC, when electricity is really being pushed at the peak, there's a big voltage, there's a big current, there's a lot of wattage. But what about when the sine wave cycle goes through its middle, when there's temporarily, for that instant, 0 volts, 0 amps flows in at least a resistor? Yes? Is there any power being generated? Is any energy being transformed, transferred, traveling? No. When the AC signal goes through 0, there's nothing. By the way, when the AC signal goes to the negative maximum, you've got negative max voltage, negative max current. There's still power. There's a lot of power. There's just as much power as at the peak of the sine wave signal. But if we want to find out how much your electricity bill is going to be, just looking at peak voltage, peak current, as we often do on the graph of a sine wave, that's not going to do it, because all but at that one peak instant, the sine wave does not have that peak wattage. When the electricity is pushing, we have to have a way of averaging out how much push there is. That's something called RMS. RMS stands for root mean square. Root mean square current or voltage is the amplitude, this is the definition of it. The amplitude of, this is the amplitude of alternating current, the amplitude of AC, that would cause the same power, the same heating rate, same transfer of energy in the same resistor. In other words, if you plug in your toaster and supply it with 120 volts AC, that's an RMS. You would plug it into a 120 volt battery. If you did that, it would generate the same effect, the same amount of heat. Let me say that again, but backwards. If you had a 120 volt battery, you plug your toaster into that 120 volt battery, it would dissipate 120. So whatever wattage that resistance of that toaster would give. When we talk about 120 volt alternating current, we're talking about the RMS, the averaged voltage, the root mean square voltage. The peak value, if you were looking at a graph, what you would naively think is the amplitude of the sine wave. That's actually 178, if I recall correctly, 178 volts. So in math class, once upon a time, if you have graphed y equals sine x, you look at amplitude as the height of the wave, not with RMS, baby. To get RMS, you have the mathematical equation. RMS value is 71% of 0.707 times the peak value. Voltage RMS, anything RMS is 0.707 times the peak value. If you are trying to calculate resistance, divide both sides by both sides, the 0.707 cancels out. You don't need to care if you've got RMS and RMS, if you got peak and peak. Resistance, it don't matter. A resistor is going to do the same thing with whichever way you measure it. But if I ask you to calculate the wattage, the power of a device, which is what you care about for your electric bill, you must always convert whatever you are given, you must make sure you are multiplying voltage times current in RMS versions. 120 volts is not the max strength of the sine wave in your wall outlet. Okay, so please take 1 second, turn to your neighbor and summarize. What is the point here? What is RMS? Tell each other. Average voltage of a sine is 0. The peak is the raw amplitude. That's what I call V peak or whatever. RMS is actually a value down here. 71% of the peak is the time averaged max that we need. You can actually prove this with math, but This is the RMS value. This height is 71% of this height. Now let me summarize in my words. There's more than one way to measure how strong a sine is. You could talk about its max height. That's what I call peak voltage. Or you could talk about RMS, which is defined as 70.707, 70.7% of the peak value. Always use the RMS when you're calculating how many watts an electrical appliance uses. That will give you correct answers. And what about resistance? Can I use RMS? Yes. Can I use peak? Yes, it doesn't matter. If I ask you for the resistance of a resistor and I give you RMSs or peaks or whatever, as long as you're consistent, as long as you use both current and voltage as RMS or both current and voltage as peak, you got to be internally consistent. Pick a measurement and use it. Pick a way of measuring, a way of describing strength and use it. As long as you're consistent, you'll get the same answer. Mitzi, you don't like that. Tell me why. Ask me. Who's got a graphing calculator handy? Now you can do this on the computer too if you must. Go to Wolfram Alpha or whatever. Y equals 2 sine x. So it look like. Look, use the cursor to scroll around the graph. What is the biggest value that 2 sine x takes on? 2. What is the smallest, the deepest negative value that 2 sine x takes on? -2. We usually, in math class, we always talk about the amplitude of that sine wave as the number multiplying sine as the maximum or the absolute value of the minimum value that sine has. Again, I'm saying that there is another way to describe strength, oomph, of a sine wave, and that is you calculate it by taking 70.7% 0.707 times the peak value. You could also, there's more than this, there are more than 2 ways to describe it. Some people also talk about the peak to peak, top minus bottom, as the oomph of the sine wave. That can be important in some contexts. The average of the sine wave, if we've got true AC, the average of the sine wave is always 0. You're wiggling, sometimes pushing this way, sometimes pushing that way, but on average, it's not pushing at all. On average, the center line of sine is 0. So again, what I want you to remember, what I want you to think about, what I want you to be able how I want you to think about this is RMS is another way of describing strength of something, and you convert from peak to RMS with that equation. You can, God willing, solve that equation for RMS. You can solve that equation for peak, just divide both sides by the same, yeah? And if you use RMS for power, use RMS for the voltage times current, you are guaranteed to get the righto resulto. Okay, that said, Mitzi, have you thought of a question? There is no DC here. There is no DC. In your graph that you're drawing pure DC. AC, pure AC. I've got a sine. This is the function y equals sine x. If you draw DC, you just have a flat level. I am indicating, I see what you're saying. This is not a function that I'm drawing. The dotted line is saying this is the amplitude that corresponds to 70% of peak, roughly, the amplitude that corresponds to how much DC it would take to get an average to be able to talk about the power in the same way that we talk about with same formulas. If you want power to equal V times I, in DC, that just works. DC has a single value. Since AC wiggles, we have to convert to RMS before we do V times I. Yeah. Yeah. Feel better? Yeah. Okay. Ba, ba, ba. So let's try doing a thing. Here's a graph of voltage versus time. Here's 3 sine something x. I want you to spend a few seconds, or milliseconds in this case, and find what is the RMS voltage, what is the peak voltage, what is the period, what is the frequency for this graph. No Google form today. You don't need to put these in the Google form. Calculate it. I'm going to look at your faces to see when you're done. Then you can judge yourself. Go back to your definitions if you need. Seven minutes? Okay. We're going to look at a pretty launch in a few minutes. Assuming it goes off on time, too. How you guys feel? Are you done? Still working? Okay, well, let's do it. Peak voltage and period are the fastest. You don't have to do these in any particular order. I see these immediately. I see these. Peak voltage. How do you find the voltage of the peak of the sine wave? You look at the graph. The maximum value that the voltage has, the sine wave goes up to 3. That's V peak. I hope that you answered 3 volts. RMS voltage is, we use the equation, 0.707 times peak gives the RMS way. If I multiply 3 by 0.707, I get roughly 2.1 volts. Sometimes I write this as volts RMS. Just to remind myself, darn it, this is not just any voltage, this is voltage measured in RMS. Properly speaking, volts are volts are volts. There's no difference. But it's a practical help. Okay, period. I look at period. How do I find the period? I look at the same place on the cycle. How long does it take to fully repeat? If you put 0.1 seconds, girlfriend, you started at a peak at 0.1 seconds. You're not at a peak. When do you get back to a peak again? At 0.08 seconds. And if 0.08 seconds is one cycle, then 1 over 0.08 seconds is the number of cycles that you get in 1 second. You get 12 and a half, which I'm going to round to 13. 13 times in 1 second, 0.08 seconds for one time. These add up. Don't multiply up. One is the reciprocal of the other. Questions about this? Did you get this? Question. Multiplied it by 0.707. That's the formula from the previous page. Write that down. But the amplitude is just the peak value. It's right there. Just read it. DC is what we've been doing this whole time with electricity. You've got a voltage. It stays that voltage. We apply a steady battery to something. DC is what comes out of batteries. Constant level. AC is a wiggle. Wiggle, wiggle, wiggle. Questions? Keep asking. Come at me, bro. Mitzi. Yeah, yeah. So if I wanted, if this is running a heater, a space heater, whatever, 3 volts, that's not going to do much. If you wanted to run the space heater on a battery that generates the same electrical effect, you'd have to provide that graph of DC. Both of these do the same thing. Steady line, that's DC, at the RMS voltage level. Or a wiggle. So the first word here should say AC, the amplitude of alternating current that would dissipate the same direct current in a given load. Tell me this. Riddle me this, Batman. I'll tell you that volts times amps in RMS way of writing is 1900. Can you find la resistance of this heater? Use the formulas that we've got down. P equals VI and V equals IR. Womp womp.
We can just go back up. We could.
Rewind time.
Just a little, yeah.
We didn't know. We were in a 10 kids.
Hey, you guys know why it looks like it's going down? It's going up. It is going up. But the Earth is curved. So as it goes over the horizon higher and higher and higher, following the curvature of the Earth, you don't go straight away from the Earth. Launching, play some Kerbal Space Program and you'll find out. You don't launch straight up. You follow the rotation of the Earth, always east to west, as you're going up. So you go up and over to get into an orbit. This is following the curvature of the Earth is why it looks like it's going vertically down. I guess actually it is going, if we were a flat Earth, this would be going in the downward direction, but we're curved. So following around the horizon does appear to be going down from our perspective. Its altitude is getting bigger, I promise. Okay. Questions about what this is? This is a rocket. There's a rocket going to the moon if all goes well. You done? Did you get this? 8-ish? 7.5? Good. Please note, again, when I convert, when I use wattage equals volts times amps, when I convert to find amps, I'm still in RMS land. This 15.8 amps, there will be times when the current is bigger than this. If you got a fuse on this sucker, you better provide more than a 15.8 amp fuse or that fuse is going to blow. But 15.8 amps is a way of measuring this, even if it's not the peak height of this. Once you've got the amperage, it doesn't matter whether we're in RMS or peak values. Excuse me. The ratio of RMS over RMS will give you the correct resistance. As long as they're both RMS or both peak. That's good? Hit me.
Or the 60 hertz?
Yes. Time has nothing to do with height. I will remind you from the previous part that we found can you tell me the maximum current? What the hell? Maximum current and find the maximum voltage. Sure. Sure. Oh, 170. But it was 178. Whatever.
Because it's in watts, we assume that it's AC and we don't have to convert.
Wattage applies to anything. But if I'm talking, I'll tell you if we're talking about DC or AC. If it's ordinary household appliances that you plug into the wall, it's always AC. If I'm talking about a battery powered toy, that's always DC. You look at the source of it. And if you are confused, if I give you a problem on a test and don't explicitly state, you can ask and I'll tell you. Well, if you don't know whether I'm talking about DC or AC and I tell you wattage, you can use the same formula to get the voltage, the current, if you're given the current and voltage respectively. But how to interpret that? For a DC, if you've got a DC power, you're getting the DC voltage, the DC current, the ordinary voltage and current that we've been talking about. For AC, there are two different ways of measuring the strength of the AC wiggle. So once I give you a wattage, you should think voltage and current are going to come out of this in RMS. This is going to give me, AC wattage is always going to be in RMS. Then you may or may not want to convert to peak. Last question. Think about this for a second. Oh, did you get these values or am I rushing you? Yeah? These were given on the previous slide. 3 slides ago. This is what it means to be RMS. RMS is 0.707 times the peak value. RMS is 0.707 times the peak value. Write those down. Those are important. All right. So. You guys okay with 22 and 170 respectively? You able to get this? Okay, so tell me this, or riddle me this, Batman, as I am fond of saying. This is the maximum value of the sine wave voltage, the maximum value of the sine wave current. I said that backwards. At the instant when voltage is maximum, what's the power at that instant? Calculate. Tell me the power at that instant. Gesundheit. What was it, 22.3? I don't need a calculator. I could do that in my head. How did I do that in my head? Hey, what's the relationship between the peak power and the average power? The peak power is exactly twice as much as the average power, or equivalently, you could say the average power is exactly half as much as the peak value. That's where the 0.707 comes from. If we've got a wiggling power transfer signal, half of its peak is its average value. It's the power that we're talking about, that we want to get, that we care about for the sake of your electric bill or whatever. It's the average power we want, not just the power at any given instant. Now it's 5 watts, now it's 0 watts, now it's back to 5 watts, now it's back to 0 watts. We want the average power to get what your average energy bill is going to be. Unless you only turn on your device for a 60th of a second or less, You don't care about the fact that it's going up and down. You want its average power. This is how to get it. Does that make any sense? More or less? Which I rounded 0.707. That's actually 1 over square root 2, by the way, if you care. You might care. Microelectronics. You'll deal with AC. So you do not need to memorize at all that peak instantaneous power is twice the average power. However, I would like you to recognize that there is such thing as, you do need to know the idea that power does have a sine wave sort of as well. It wiggles up and down. When the voltage is high, the power is high. When the voltage is low, the power is low. When we're talking about the power of this electronic device, though, this pulls 3,000 watts or whatever, we don't want the instantaneous power. We want an averaged amount of power because we usually run an electrical appliance for many, many times a 60th of a second. They are more than meets the eye. They are transformers. Let's talk about them for a second. No, not that kind of transformer. A transformer is an electrical device which can change voltage. I mean, if you've got several resistors in series, you can get 1 volt out of a 10-volt battery, right? You can just dissipate 9 of those volts, then you've got 1 volt left for something. Well, that's very wasteful. You're absorbing 90% of your initial voltage level as heat. What if you wanted to increase the voltage? There's no possible way you could take resistors and get more volts out than you put in. But there is some magics. With the magic of transformers, I'm not going to teach you how, but I will say that the physics of transformers is exactly what we just did. It is exactly Faraday's law, Lenz's law. The voltage inside a transformer comes from induced voltage. They're magnetic devices. Transformer magnetically, not magically, magnetically transfers energy. The inside are 2 magnets, 2 coils that feel the magnetic field inside them. The transformer equation, here is the one and only equation you have to know about. No, there are 2. Transformer equation that you need to, oh, for God's sake, 2 typos. Transformer equation that you need to know is that the voltage ratio is directly proportional to the turns ratio. That is to say, if you've got coil 1 has twice as many turns as coil 2, then coil 1's going to have twice as many volts as coil 2. If I've got a coil with 5 turns and I put some voltage on that, AC voltage only works with AC, and the output has 10 turns, I'm going to get twice as much amplitude of voltage out. You can plug that in. If I've got 5 turns in and 10 turns out, whatever I put in here, there's going to be twice as much voltage there. 120 volts will become 240 volts. Or, say you've got 12,000 volts that you want to become 120 volts. This is actually practical. This is what your electrical power grid does. The transformers outside your house do this. The power lines have more than 120 volts on them. I don't know the exact number, but say it's 12,000. There is inside those transformers, say, 1 turn and 100 turns. 100 turns on the high voltage side, 1 turn on the low voltage side. You get 12,000 volts turned into 120 volts. You can't get something for nothing. So, look carefully. There was a freaking typo. These should say ends as well. Sorry. The current is flipped. If you got twice as much voltage, you get half as much current. If you've got 10 times the voltage, you get 1/10 the current out. If you bring the voltage down, the current goes up by the same ratio, or by the reciprocal of that ratio. I don't memorize equations whenever I can get away with it. How I store this internally in my head, how I encourage you to memorize this, is voltage multiplies if the turns multiply. Current does the opposite of voltage. If you've got twice as many output turns, you'll have twice as much voltage, you'll have half as much current. If you think about it that way, you have less symbols, you have fewer things to manipulate. There will be fewer screw-ups, I promise. And again, one more time, this is magnetic. This is Faraday's law. Proving it, showing you how the mathematics, well, I think the math of Faraday's law was as far as we want to go in 112. I don't think it would be beneficial to actually show this, but I promise you the mathematics causes this effect exactly. Terminology. Step up means voltage goes up. Step down means voltage goes down. If I refer to a step-up transformer with a 1:10 turns ratio, I'm talking about the voltage increases by a factor of 10. If I talk about a step-down transformer with a 10:1 turns ratio, I'm saying it steps down by a factor, it divides by 10. You don't have to memorize 10:1, 1:10, which is the input, which is the output. You can just look at, am I talking about step up or step down? If I use these words, I multiply the voltage by that factor for step up. I divide the voltage by that factor for step down. And current does the opposite. I always think of voltage and then current does the opposite. Your household electronics, your charger bricks, the stuff in most of your electronics at your house that plugs into the wall always has step up or step down. What do you think? Step down. Normal electricity levels for all the circuits we did in lab, those battery powered things, 1 volt, 10 volts. My examples are realistic, by the way. We did things like 12-volt batteries a bunch because that's a very common level that electronic components like to deal with. The inside of your desktop computer has 12-volt, 6-volt, 3.3-volt levels inside. A few volts is reasonable. 120 volts, holy crap! That's a lot of voltage. We step this down so that the internals of your circuitry are receiving a happy level that they like. Except for me, because I like vacuum tubes, because I like vintage electronics. In the olden days, 120 volts? What 120 volts? 600's where it's at, baby! We use step-up transformers in my ham radio because I want high voltage to run them their vacuum tubes. Oh yeah! Also, uh-oh, if you shock yourself, because large amount of voltage means it's a large amount of possibility of dying. Okay. Last terminology here. Primary, secondary. Which do you think is the first and which do you think is the second? Primary means first, secondary means two. Primary is the input side, secondary is the output side. Does that kind of click? So which is the input, 120 or 100? Yeah, the input is what you plug into the wall. Okay, calculate this. Ready, set, go. If you get a huge number, you might be right. It is reasonable for transformers to have a butt ton of turns. Part of why they can be really heavy. Part. What you got? I rounded. I always round. You got 40-ish thousand. Yeah. Here's how I think about it to do this efficiently. Step up transform brings voltage up. Duh, right? I mean, look, the voltage goes up. So the turns go up. So I multiply. That's it. You can plug into the equation N1 over N2 is V1 over V2. By the way, it doesn't matter which one is 1 and which one is 2. You just got to match input with input, output with output. Be consistent for 1 and 2. N1 over N2 equals V1 over V2. Solve for V2. Blah. Tedious, annoying, whatever. Who cares? It's easy to mess up that equation. Turns ratio is 833, and the turns go up, so 833 times 50. Do you smell what I'm stepping in? You hear what I'm saying? Okay, so you've got 50 turns in the primary, 41,700 turns in the secondary. The last question is how much current flows in the secondary? Okay. As long as you're consistent, V2 over V1, N2 over N1, V1 over V2, N1 over N2. Doesn't matter as long as you're consistent. Yeah, that's fine. As long as you're consistent, picking one as input, two as output, or one as output, two as input, you'll get the right answer. Who got 12 milliamps? 0.012. Yeah. Okay, I want to emphasize something. Is this a lot of electricity? 0.012? I'm sure it doesn't sound like a big number. This is a lot of electricity, though. How many watts is this? 120 volts times 10 amps on the input side, more than 1,000 watts of electricity. I mean, that's your oven puts out more than this, but this is a decent amount of electrical power for realsies. Current alone does not tell the full story. There may be very few electrons passing per second, but 100,000 volts, those electrons have real punch. So voltage and current together tell the full story of how oomphy the electricity is. Hey, how many of you are in my Wednesday lab? I should remember just by face, but okay. Y'all, based on the demonstration I did, you can understand. Stick around for 2 seconds. I'm going to call it early for everyone else. Oh, MCAT students, you may wish to listen. The connection between Faraday and this is something I only taught them, but the doctors may also wish to hear. Anyway, if you're not in either of those groups, you are welcome to get out. I love you. Or you could stay. Oh, hey, you just want to stay? Okay, what I'm about to tell you, is to connect two topics. Since I did not present this link in lecture, I'm not going to test on this. But if you were in my lecture, you saw a very important discovery. Induced voltage can affect the current that made it, the voltage that made it. The original coil is affected by the induced voltage. Yeah, my Wednesday lab, you remember seeing that? The total current that flowed was not. Making them the go-to play for everyone. Okay, let's try this again. The current that actually flowed was not just straight from the applied voltage. There were really two voltages fighting, adding together. You get a very different result. The applied voltage and the induced voltage together drove that current, and not at the same time. So the big takeaway, the point I hope you get, is that induced voltage pushes on the original current that produced it, as well as any other coils that are nearby. Now, think just for a second. Every single turn, this is something from last week's quiz and homework, I think. Every single turn feels the induced voltage. If you calculate delta phi over delta t, the induced voltage, you're calculating for one turn. If you have 800 turns, you would multiply each turn gets so many volts. 50 volts times 100 turns is there'd be 5,000 volts in that whole coil feeling it. Well, again, that voltage is in both the primary and the secondary, and your mama's coil. Whatever coils of wire are nearby in that magnetic field are going to get, each turn is going to feel that same voltage. So, the idea behind the transformer equation ain't nothing but saying the voltage per turn, let me write this down, V2 over V1 equals N2 over N1. Solve for V2 over N2. If I multiply by V1, N1 and divide both sides by, look, you can also just write this as V2 over N2, right? V1 over N1. This is just the This is just volts per each turn. That's delta phi over delta t that we've been spent 3 lectures talking about. Well, 1 and 2 halves. We say that the voltage, delta phi over delta t, the induced voltage simply exists, and every turn picks up V2 over N2, V1 over N1, V3 over N3. There could be 3 output transformers. If you've got a butt ton of turns, you multiply that by the number of turns, and that's your total voltage. You put 120 volts total in, it pushes on 1 coil, it pushes on 10 coils with the same amount of push per coil, and then lots of coils multiply up. You got more coils in the output than the input. You've got more times that the same induced voltage is being felt. That's all. And hopefully that made any kind of sense for those of you who didn't see what I said.